Hey guys, so how many times have you been on the field and you just got done with your polar alignment and you get ready to do a 1, 2, or 3-star alignment, or you're getting ready to get centered on your object? Have you ever looked at the numbers on your keypad or in Stellarium or in CartCL and wonder what exactly do those numbers mean? Worse yet, have you ever been out of the field and that one know-it-all guy comes up to you and says, "You don't need to be looking for that in Stellarium. You need to be looking for that in RA and DEC." The hell does that mean? Know-it-all.
Let's do a quick review. The Earth, of course, orbits around the Sun, taking 365 days to complete a full drive-by. The Earth, along with other planets, orbit the Sun basically in a flat sort of a plane. We call this the ecliptic plane. The Earth is also spinning around happily on its own, creating cool stuff like gravity, and it spins on its axis, the north axis and the south axis, in other words, the poles. That spin is a little off true up and down in relation to the ecliptic plane. We are slightly skewed off of center. Therefore, the Earth's equator does not fall in line with the ecliptic plane, which is shown here in green. Since we use RA and DEC coordinates in respect to Earth-based coordinates, we have to draw an imaginary line from our equator out the sides of the Earth at its respective degree of angle, all the way out to infinity. Yeah, we basically invented the rules to play by here. Now be sure to remember this celestial equator thingy. It's going to come up again shortly. Anyway, on Earth, we use a grid coordinate system. It plays a vital role in GPS and navigation. We call it longitude and latitude. You know, seriously, I could never remember which was which back in school. It used to confuse the living crap out of me. Anyway, latitude, or think altitude, are the imaginary lines that circle the Earth east to west. I say think altitude because you can think of the lines as height above the equator or height below the equator. The equator is indicated as 0 degrees and is exactly around the belt of the Earth. Longitude is the imaginary lines running north to south, or vice versa, depending on where you're at or from, and they circle the Earth from top to bottom. The prime meridian is considered 0 degrees, which is the starting longitudinal line running through Greenwich. The prime meridian and the equator basically divide the Earth up into quadrants or hemispheres: north, south, east, and western hemispheres. This creates basically 90-degree quadrants from the equator to the poles for us to use as the coordinate system. Now while we're here, start thinking of RA or right ascension as longitude and DEC or declination as is to latitude. Yeah, I know. I promise it'll sort of make sense later. Longitudinally, the U.S. is west of the prime meridian, so we are minus or negative degrees from the prime meridian, while Europe and Asia are positive or plus to the east of the meridian. Concerning latitude, the northern hemisphere is, of course, above the equator and is considered positive or plus, while the southern hemisphere is negative or minus. Note that an area like South America kind of gets a bad rap as they are both minus south and minus east. Tough break, guys. At some point in human history, it was finally correctly determined that we orbit the sun and the stars are basically static, which finally became widely accepted after several unfortunate astronomers were shackled or put on trial for heresy. So trying to figure out where things were seen and at what time of year and during what season, we had to develop a way to map and determine future positioning of objects in the night sky. Obviously, coming up with constellations helped to map the sky, and that in which eventually led to cool gadgets for Earth positioning like the sextant. You know, think about it. The sextant and that dude who knew how to use it were like gold. I mean, he was basically your GPS. You never left port without him. Years ago, and I mean like years ago, the celestial sphere idea was created. Basically, what we do is project the Earth coordinate system up into space into a big sphere surrounding the Earth. Thus begins the idea of RA and DEC. This helps us to place objects in the sky as far as where they will be at a certain degree by time, position, and angle in relation to the viewer. Besides, we also have to take into account that the Earth spins every 24 hours while still rotating around the Sun and is always changing position. I mean, those dang stars just keep on moving around on us. I mean, geez, what the heck, man? Anyway, maybe now you start to get the idea of why Betelgeuse is never in the same place every single night year-round. Right ascension is pretty much easy to understand. Right ascension basically equates to time. Right ascension is measured in hours, minutes, and seconds. Basically, every year on March 21st, it's the 20th, 21st, right in that area, we go through what's called the vernal equinox. Every year, March 21st. On March 21st of that year, the sun, as it crosses the prime meridian, is set to 0 hours, 0 minutes, 0 seconds. Now, it's something like 23 hours, 59 minutes, 59 seconds, something like that. Basically, we just say 0 hours, right ascension, on March 21st. All objects in the night sky, because they don't move, we do, is measured in time behind the sun. So for instance, Sirius on March 21st is basically 6 hours, 45 minutes behind the sun. Well, to make the math easier, just round to the nearest even hour. So for Sirius, let's just say 6 hours. Capella, I think, is 5 hours, 55 minutes, so basically 6 hours. Arcturus, as measured, March 21st, is 14 hours. Now, as the years progress, or as the year progresses, as we go through month by month, we're changing position in the orbit of the sun in relation to the sun as we go around. So every 30 days, roughly, time changes by 2 hours as objects are considered behind the sun because we are moving. So on 4/21, and let's just go and write this out. On 4/21, we've rotated roughly 30 degrees around the sun, which equates to 2 hours. At that point, Sirius is basically 4 hours behind the sun. In May, it becomes 2 hours behind the sun. June, it's at 0 hours, or basically right behind, above, or somewhere very, very close to where the sun is in its RA. Same thing for Arcturus. Every 2 hours, or every month, every 30 days, we change by 2 hours. So basically what this means is as the sun rises in the east, let's just say this is where we're standing. As the sun rises in the east at 6 a.m. in the morning, Sirius is 6 hours behind it. When the sun crosses your meridian, let's say it's here, 12 o'clock. At that point, Sirius is roughly just starting to come over the horizon, is just starting to come up. There's Sirius. So as the sun sets on 3/21 here in the west, Sirius will be just crossing the meridian 6 hours later. This is considered to be 12 hours. Each side, or each 90 degrees, is 6 hours. So in April, as the sun comes up and hits the meridian at 12 noon, Sirius will be not here, but actually here. So during these months, we're not going to see Sirius in the sky. It's going to be washed out because it's daylight. Now Arcturus, 14 hours behind the sun, which actually makes it look like it's in front of the sun, so to speak. April, 12 hours. May, 10 hours. June, 8 hours. So as the sun is setting in June, Arcturus will be 8 hours behind the sun, which should still be visible at night. When we hit July, it'll be 6 hours behind the sun. August, 4 hours. You get the idea. So just always remember, March 21st, the vernal equinox, RA of the sun, 0 hours, everything is measured behind the sun on that date. So declination. Declination, or what we call angle of or angle of declination, is based off our longitudinal lines. As the Earth is, probably could have just drawn a circle first, but here's our equator. Again, anything above the equator is a positive angle. Anything below the equator is a negative angle. So if you remember from earlier, we were talking about, because our equator is not lined up with the ecliptical plane, our equator, we have the celestial equator from where we look at, which is what we base the celestial sphere off of. This is going to be your North Pole, South Pole. I'm basically standing here, and I'm roughly at 35 degrees longitude. So if an object is given its angle, its angle of declination, so let's say Sirius, as a for instance, its angle of declination is negative 16 degrees by 42 minutes. And actually we say arc minutes. So degrees, arc minutes, and then it becomes arc seconds, whatever that number may be. So negative 16 degrees angle of declination is going to be below the equator. So Sirius, let's say 16 degrees, is roughly there, let's just say, okay? 16 degrees below the celestial equator. So I can still see Sirius at this point, because Sirius is way, way far out there. So even though it's below me and below my celestial equator, I should still be able to see it based on where I'm at in my degrees. Now, which way would I look? Obviously, I would look towards the south, towards the equator, in order to say Sirius. So how do I know exactly what 16 degrees are based off of where I'm at? Well, from where I'm standing, and remember I'm looking up towards my meridian, I'm at 35 degrees. So basically the formula to figure out where you're going to look is that you take your angle of look at that. Take your angle of declination minus your position, 35 degrees. So at negative 16 minus my position of 35 is basically going to mean negative 18 degrees from where I'm at. So if I look straight up in the sky, boop, 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 to my meridian, or zenith, is what we're calling that, the zenith, I'm going to look 18 degrees to the south in order to be able to see Sirius. Let's take another one as an example. Let's take Vega. Vega, angle of declination is 38 degrees. 38 degrees and 47 arc minutes, I believe, something like that. So basically 38, I'm already standing at 35. Where am I going to look? Well, it's positive. So for positive, I'm going to look towards the north. So 3 degrees off, just barely, right off from where I'm looking at, I should be able to see Vega at a declination angle of 38.
So hopefully that cleared everything up, and now you have some understanding of what RA and DEC is, or at least now you know what those numbers and little symbols and stuff mean on your hand controller or in your computer. Hopefully I didn't confuse you too badly. And if that guy does ever come back up to you, you know, the know-it-all fox, you can tell him, I know what RA and DEC is. Right? Right. Well, mate, you don't know anything about RA and DEC. How the hell did I come up with an Australian accent? Is that even Australian? Ah! Rabbit attack! Rabbit fox attack! It's been a hard day's night, and I've been working like a fox. This is the rattiest, nastiest toy that my dog has, and I'm using it. It's stupid. Yeah, so this is still airing, but you gotta, right now it's right now, so you wanna fast forward it to nighttime. But wow, look how many days are going by there. Look at that. Oh God, it won't stop. Grown man playing with stuffed toys for YouTube about astronomy and astroimaging. I have no life.